Okay, let's dive right into this explainer and uncover the secret engineering formulas that literally dictate every single bump, curve, and signal of your daily commute. I mean, have you ever wondered why you intuitively slow down on a specific curve? Or why a highway feels effortlessly smooth while a local road feels completely different? Well, it is all completely by design, right down to the exact millimeter.
To figure out how they do this, we're using a literal masterclass blueprint. We're pulling straight from the Civil Engineering Exam Question Bank from SRM Valuemai Engineering College, prepared by Dr. P. Nilayamagam. This document is an absolute goldmine. It's the actual material used to train the next generation of engineers, and today it's going to act as our map to decode the built environment around us.
So, here is our roadmap for this explainer. First, designing the perfect highway. Second, taming the traffic operations. Third, the anatomy of pavements. Fourth, engineering the railway track. And finally, controlling the trains. Consider this your crash course through these 5 key units. We're going to move from the asphalt of complex highways and urban traffic systems, dig into the actual anatomy of the pavement below us, and then transition all the way to the heavy steel of the railways. Let's just get right to it.
Unit 1. Designing the perfect highway. We're starting our journey on the road, where engineers have to calculate everything from hairpin bends to grade compensation, way before a single drop of asphalt is ever poured.
Think about this. Why do we actually widen roads at curves? It turns out it comes down to something called the PIV theory. That's perception, intellection, emotion, and volition. Engineers aren't just measuring the physical size of your car. They actually widen these curves to accommodate human psychology. They literally factor in the physical time it takes for a driver to perceive a curve, process that information, and then physically turn the steering wheel.
And without super elevation, your car would be in serious trouble. Imagine taking a horizontal curve with a 200-meter radius. To prevent vehicles from just flying off the road due to centrifugal force, engineers actually bank the road. According to the source data, this banking, or super elevation, is mathematically capped at a 1 in 15 ratio for certain highways. It's this incredibly precise balance between gravity, friction, and the design speed of the highway itself.
But engineers don't just draw lines on a map. They use really strict demographic data, like the historical frameworks from the Bombay Road Plan, to allocate highway lengths. They use distribution data based on town populations, like the ranges we're talking about here, to calculate exactly how many kilometers of national and state highways are actually required to connect communities efficiently. It's all a numbers game.
Unit 2. Taming the traffic operations. So let's move to our second unit and see how all this geometry builds into managing the absolute chaos of the vehicles actually using these roads.
So how do we prevent road accidents? To solve this literal life-or-death exam question, engineers definitely don't just guess. They conduct extensive origin and destination surveys to see exactly where traffic is flowing. Then they draw incredibly complex collision and condition diagrams, mapping out the physical environment of an intersection against historical crash data to pinpoint exactly what is going wrong. When they collect all this data, we have to distinguish between 2 totally different but crucial metrics. You've got time mean speed, which measures the average speed of all vehicles passing a single fixed point on the road. But then you have space mean speed, which measures the average speed of all vehicles over a specific length of highway at a given instant. Understanding the difference between a quick snapshot and a whole stretch of road is absolutely vital for accurately calculating highway capacity.
Now, armed with that speed and volume data, engineers start deploying their tools. By implementing specific features, like rotary intersections or raised channelizing islands, traffic engineers physically force chaotic traffic into organized streams. Sometimes, literally just a painted road marking or a physical barrier drastically reduces the number of conflict points where accidents could happen.
And have you ever wondered how speed limits are actually chosen? It's not arbitrary. Engineers rely heavily on the 85th percentile speed. That is the speed at or below which 85% of vehicles travel in free-flowing conditions. Instead of just picking a number out of thin air, they use this metric to set realistic, safe speed limits that the vast majority of drivers naturally feel comfortable obeying anyway.
Unit 3. Anatomy of pavements. Okay, let's dive into the actual ground beneath our tires and explore the materials making up the road surface. A fundamental civil engineering choice basically comes down to flexible pavements versus rigid pavements. Flexible pavements, like your typical asphalt roads, distribute heavy wheel loads downward through multiple granular layers, your subbase, your base, and your surface. Rigid pavements, on the other hand, are made of cement concrete. They behave like a solid slab, relying entirely on the slab's flexural strength to bridge over any minor weaknesses in the soil below.
And this is where the California Bearing Ratio, or CBR, comes into play. It completely dictates the required thickness of the road. If a natural soil subgrade has a super low CBR of just 5%, it's going to require a massive structural buildup. But if you have a strong upper layer like water-bound macadam, it boasts a CBR of 80%. This penetration test basically tells the engineer exactly how much the ground can take before it yields.
But hey, even rigid concrete slabs aren't invincible. This really provocative question from the exam highlights a massive vulnerability known as mud pumping. This happens when water gets trapped under a rigid concrete pavement. As heavy trucks roll over the joints, the slab deflects, literally pumping the wet, muddy subgrade soil right out from beneath the concrete through the cracks. It's like a giant, dirty sponge. Over time, the slab loses its support and just breaks. Preventing it requires absolutely impeccable drainage and strong subbases.
Unit 4. Engineering the railway track. Let's leave the asphalt behind and transition to the heavy, ironclad world of railway engineering. The scale here is just massive.
While roads offer incredible point-to-point flexibility, railways are the unmatched champions of national economic development. They boast immense hauling capacity for both freight and urban mass transit. But they do have some inherent operational weaknesses, like massive initial capital costs, and of course, a rigid track system that cannot easily bypass an obstruction.
What engineers call the permanent way is this highly synchronized system. The steel rails transfer the train's weight down to the sleepers, those crossbeams. Then, the sleepers distribute that load into the crushed stone ballast, which provides elasticity to absorb all those massive vibrations. The crazy part? Even a minor flaw here, like rails expanding and creeping forward or developing sharp kinks, can lead to a catastrophic derailment.
Unit 5. Controlling the trains. For our final unit, we're going to explore how engineers manage the sheer kinetic energy of moving trains through complex networks of yards, points, and crossings.
You can't just steer a train left or right like a car. You rely entirely on the track to guide you. That is exactly where interlocking comes in. It's an absolute fail-safe system. It mechanically or electrically links the track switches, the points, with the visual signals. It makes it physically impossible for a signal to show green if the track switches ahead are set to route two trains onto a collision course.
Getting a train moving and keeping it moving is an immense physics problem. Engineers have to mathematically balance a locomotive's tractive effort against a whole host of opposing forces. According to our syllabus source, they are calculating the exact rolling resistance of 20-ton wagons, the steepness of rising gradients, like a 1 in 200 climb, and the friction of negotiating a 4-degree curve, all just to ensure the train has enough power to prevent stalling out on the main line.
And track maintenance isn't just reacting to a broken rail, it's this relentless scheduled 12-month cycle. Take trough packing, for example. It's an annual, through-maintenance process where crews literally manually open up the track, square up the sleepers, and meticulously repack the stone ballast beneath them to restore the track's perfect geometric alignment. It is hard, continuous work. So whether you're navigating a channelized rotary intersection in your car or riding over deep-screened railway ballast on a high-speed commuter train, your safety and efficiency are governed by the rigorous math and physics we've explored today. Next time you're on your commute, just look out the window and try to spot the hidden blueprint working all around you. It's pretty amazing when you actually know what to look for.